Okay, thanks. Thanks a lot to the organizer. Thanks, Michael, for this introduction. So today I would like to speak about this joint work together with a student of myself, that is Claudia De Lazzari, and a collaborator, that is Fulvio Gesmundo, about the dimension of tensor network varieties. So a very quick overview. I will start with some motivations, and then I will pass through some definitions, a precise definition of tensor network. I will see some properties, and then I will start discussing the problem of dimension, and I will conclude with very few questions. Okay, so motivations. My main motivations come from quantum physics. And so if you are a physicist and you want to deal with the state of particles, then you have to deal with a tensor. And this tensor may live in a huge ambient space, that is the space of where all the tensors live. And if you really want to work with that, then this becomes very soon intractable because you have a huge number of variables. So if you really would like to have a good parameterization of the tensor you are interested in, that reduce the number of parameters that you need to use every time you work with your state. And moreover, something that is very interesting from the quantum physical point of view is how the particles in their system are related. And this way of, and how they interact to each other. This is called the entanglement of the state. I'm not going to be precise at all about the definition of entanglement because it's not the topic of my talk. It's just a motivation. The point is that they would like to see their tensor as written as a linear combination of pure tensors. So tensors that you can write as an element in the first vector space, in the second vector space, in the third vector space, and so on. And with here taking an orthonormal basis and with the coefficient to be real and positive numbers. So why tensor networks helps in this direction? Okay, let's see a very baby case as an example. The first baby case is the multiplication of two matrices. So assume that you have a matrix A and a matrix B and you want to multiply them. So a way I've seen the first time from physicists to represent this product is to take your matrix A to live in some space C and one tensor Cn, and you want to multiply it with another matrix that is the matrix B that sits inside Cn tensor Cn2. And when you make this product, what you do is just you contract along the index J, where you sum them up. That is exactly where the dimension n. And the way they have to represent this fact is that they just make this edge among the two vertices. So this is a very, a very easy example. And moreover, this won't be exactly the same usage of graph that I will have. So I will, in all my talk, I won't use this graph for the matrix multiplication, but I will erase these two edges. I will simply remind that at this vertex I have attached some vector space Cn1, and that at this vertex I have attached this other vector space of dimension Cn2. So for all my talk, the matrix case will be represented by a graph of this form, and I will remember that I will contract on this edge n. So so this is good for representing the point of view of the entanglement, because from this point of view they see how the matrix interacts to each other. And this is not a definition, so I'm not using this as a definition, but just to show an example how by using this kind of construction, one can kind of show this the point of view of the entanglement. Okay, so if you are able, if the tensor you're interested in can be represented, for example, in this case, I've drawn up a sequence of matrix multiplications, so as a product of matrices, and you're able to do this by contracting every time with small dimensions, so where you put the contraction, you have small dimensions, then you're able to reduce a lot the number of parameters. with respect to the ambient space. And the punchline for them is that these matrix product states are accurate representation for states, for physical states they are interested in. So this is kind of a motivation, very vague motivation from how this kind of variety may be interested. Okay, so let's start to give a precise definition, the definition that I will use all along this talk. So first of all, I will fix a graph. So I will do this example only for simplicity, but you can think that any graph you like. Okay, so gamma is a graph. Gamma is a graph and it has some vertices and some edges. Then you fix some weights. So now you take a weight graph. So you fix a weight, say M1, and another weight M2, and another weight M3 attached to each edge. Then you consider the identity matrix for each of these weights. And so the identity matrix is a matrix that goes from CM1 to CM1. This goes from CM2 to CM2. This goes from CM3 to CM3. And then you take you tensor, so you have all these identity matrices and you tensor them all together. In this way, you have the tensor product of all the identity matrices along the edges. Now, I don't want to think this tensor as an element of this space where it naturally lives, but I want to regroup every all the vector spaces that are incident at the same vertex. So I regroup all the vector spaces incident to the same vertex. So I regroup C3 with CM1, CM1 with CM2, and CM3 with CM2, and I call this space W1. This I call W2, and this I call W3. So now I think the same tensor, okay, the same tensor, but now as an element of the tensor product over the vertices of all the tensor product of the vector spaces incident at that vertex. It's the same tensor, but thought in a different, in a reordered space. This guy, the product of this identity thought in this vector space, is called the graph tensor. So let me try to convince that, no, okay, I'm not yet done with the definition of the tensor network. So this is a graph tensor. Now I want to define the variety of tensor networks. So I define the variety of tensor network living in some spaces, V1, Vd, associated to my network. Okay, so in the previous example, I had this network. So where here I had W1, W2, and W3. And now I want to take a space V1, a space V2, and a space V3, and I want to think my tensor network living in this space, the V1, tensor V2, tensor V3. And how do? I consider all the linear maps between between Wi and Vi's, and I consider the multilinear multiplication of the graph tensor that I defined before, the product of all these identity matrices by all these, the product of all these matrices. Okay, the image of this map may not be closed, it may be or may not. I'm interested in the variety, so I take this Zariski or the Euclidean closure. It doesn't matter because I did not said yet, but I'm working over the complex numbers. So I take the closure of the image of this map. This is going to be the tensor network. So the definition that I'm going to take for tensor network. Okay. Okay. So please feel free to interrupt if you want. So now I would like to try to convince in a baby example that the contraction that I've seen in the first example and this definition they agree. So let's go back to the matrix multiplication case. So in this case, I have only one edge. I fix my weight n. I take the identity here. This goes from Cm to Cm. Now I have only one edge incident in the vertex. So the first Cm is W1, the second Cm is W2. And now I consider the map that I defined before, the linear maps from the Vi's to V going to V1, V2. by acting by multilinear multiplication on the identity. Okay, so the identity, I split it as a sum of the product of the elements on the diagonal, and then I split the multilinear multiplication as the tensor product. The tensor product becomes the transpose of this matrix, and then I get exactly the multiplication of x1 and x2 as I did before. So in this case, the tensor network is the set of all matrices that can be written as a sum of product of two matrices that they agree on this identity matrix of order n. So these are all the matrices of rank at most n. In this case, this happens to be closed. So I don't have to take the closure. Okay. Okay. So why I prefer to use this description of graph tensor, because multiplying all these multilinear maps by the graph tensor is an easy computation, because the graph tensor is the product of many identity matrices. So I have a bunch of enormous numbers of zeros in that tensors. So if I want to making this multilinear multiplication, I simply have to evaluate the graph tensor. This is an easy operation. Okay. Then, of course, if you want to test if a given tensor belongs to your favorite tensor network, then what you have to do is to start enlarging those dimensions m until you get the proper multilinear maps that applied to your graph tensor give the tensor that you are looking for. And this may be difficult. Okay, this is this is something that can be difficult. But I just wanted to show that this description by using the graph tensor has this advantage that it's easy to use. Okay, so some properties of this variety. First of all, so with n's, I always indicate the dimension that I'm going to contract. That they have a name, they are called bond dimensions. Of course, you can always assume that the bond dimension are at most 2, because otherwise you're just taking the identity matrix that is just one element and there's no point to use it. And another fact is that if you have the same graph, you fix a graph, and if you fix the dimension of the vector spaces in the vector space where you're going to live, then if you take the m, these are the bond dimensions. So this say m prime 1 up to m prime k. So this is a multi-index, and the same for m. And if you fix the bond dimension to be smaller or equal, the m prime smaller or equal than the m, then the tensor network variety that you can build by taking this bond dimension, the smallest one, is going to be contained in the one that you build if you take the n's that are bigger. And you can increase the bond dimension until you reach the ambient space. So you may fill the ambient space by playing this game. Moreover, other properties is that you may also, sorry, where am I? I'm sorry. Here. Moreover, we may do some reduction. So assume that at certain vertex, you have a bunch of bond dimensions incident in that, and this is the dimension of the vector space associated to that vertex. If it happens that you have one bond dimension that is much bigger than the others, more precisely, that is bigger than the product of all the dimension of every other vector space incident in that vertex, then you may take the tensor network variety where you see this overabundant bond dimension and build it. Or maybe you can take this bond dimension to be equal to this product and build the tensor network variety with that precise bond dimension, and you get exactly the same variety. So you can reduce all the vertices to be balanced in a way. And another important reduction comes from this definition that I took from Landsberg, Chi, and Yi, that is about supercritical, subcritical vertices. That is the analogous of the overabundant vertex, but it's about the dimension of the vector space incident in that vertex. So the drawing is the same. You have a vertex, you have a bunch of bond dimensions. So these are the MIs. And then there's another dimension here, the one of the vector space incident, that is n. So now this is n that's going to play some role. If n if the dimension of n is smaller than the product of all the bond dimension, they say they call it subcritical, otherwise supercritical, and it's critical if it's both supercritical and subcritical. So a first result that we have is that we may reduce all the supercritical vertices to be critical, and the two varieties that we build in this way, they are not the same, so they do not have the same dimension, but there's a relation between the dimension of these two varieties. So this is this is the result. So this one is the variety where I have reduced the dimension of this vector space to be equal to the product of all the others if I started with a dimension n that was bigger than the product of the others, okay? That is the dimension of this variety here. So since I'm interested in studying the dimension of this variety, I may reduce to study, to eliminate all the supercritical cases to be critical, and then to study the dimension of the critical spaces, and this will give me how to find the dimension of the all supercritical cases. Okay. Okay. So this is an aside. Since
Alessandra, can I just interrupt you? There was a question on chat. Benjamin Lowitz asked, what is special about the edge n sub v?
So, I mean, so this is a vertex, and the vertex has a name, it's called V. Okay, so every vertex is, I call V1, V2, blah, 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 the vertices, and assume that this vertex is V, and that this vertex, if it is supercritical, it happens that the dimension of the spectral space incident to that vertex that I call, say, VV, if you like, and it has dimension NV, so NV is the dimension of this V sub V. If it is supercritical, in this case, it is going to be bigger or equal than the product of all the bond dimension incident in that vertex. I don't know if I answered to that. So it's not special. It's just I'm just saying every time that I have a vertex that is supercritical, I have this property, and I do it for that vertex, and then I do for all the vertices that are supercritical.
And some of the difference between the m's and the n's was that the m's were the edges that are part of your graph that you draw, right? And the n refers to the sort of the dangling edge, the one that you don't draw.
Yeah, so this was implicit. The n's are always the bond dimensions. Those that I'm going to contract with some, so it means that somewhere else there's another vector space here in my graph. And this is a vertex that is not contract. So my tensor network variety of this sits inside V, say V1, tensor, V, K, whatever.
Great, thanks.
Okay. So I said that just an aside, at a certain point, I said that once you look at the tensor network as a parameterization that I gave at the beginning, the image of that map may be closed or maybe not closed. And since I'm studying the dimension of this variety, I'm actually not interested in the fact that if it's closed or it's not closed. I'm just taking a generic element in that point. But this is a very interesting topic to see if it's closed or not closed. And there's this result again about Landsberg and G that says that if the graph is cycles, then it's closed. Otherwise, there's something in the closure. Okay. So how do I want to tackle the problem of the dimension? I want to tackle it by a very basic mathematical result, fundamental result. So every time that you have a map between two varieties and you're interested in the dimension of the closure of the image, what do? You take the dimension of the parameter space and you subtract the dimension of the fiber at the generic element. Okay, that's really how you count and this is our case. So we have a parameterization, we have a map between two spaces, and I want to study the dimension of the image. I take the dimension of the parameter space, and I want to study the dimension of the fiber. So counting this dimension, it's a formula. It's very easy. So I'm interested in the dimension of the fiber of this map. So what there is in the fiber, let's try to understand what there is in the fiber, again, from my baby example of matrix multiplication. So matrix multiplication, I have this graph that I painted here, and I have a matrix X1 and a matrix X2, and I'm multiplying them together. Of course, you understand that if here I put an invertible matrix G, and here I put its inverse, I get exactly the same image. So all the elements that are obtained by multiplying a matrix by an invertible matrix and the other one by its inverse are in the fiber. So in the fiber, I have the whole GLM orbit. Okay, and I have the GLM orbit for each edge. In this case, I have only one edge, but you understand that I can repeat the same argument for all the edges. So in the fiber, I have the product of all the GLME orbit. This is a well-known group. It's called the gauge subgroup of my graph gamma. And this was not new, okay? This was very well known from a long time, that the gauge subgroup is in the fiber. Actually, in many papers, especially in the physical ambient, it's considered to be whatever that is in the fiber. And so it's expected that in most cases, this is everything that you have in the fiber, and that the dimension of the variety we are looking for is either the ambient space, if it fills the ambient space, or the dimension of the parameter space minus the dimension of this group. Okay, that's kind of expected, but thinking in this way doesn't take count of two very important ingredients. One is that there may be some stabilizer of the action of this group, and this is going to change the dimension of the fiber. And the other thing is that there could be something more in the fiber. We know that the gauge subgroup is in the fiber because it's easy to show that it's in the fiber, but there will be something more. So these are two main issues that one has to take into account if one wants to study the dimension of this variety. So this rephrase what I just said, prove what I write here, part of our main theorem, that is that the dimension of the tensor network is smaller or equal. And by smaller or equal, I'm saying that what I'm going to say now is the dimension of the ambient space minus the dimension of the fiber. But I just said that there could be something more in the fiber. So here I can only put the minus equal. And here I wrote what I have in the fiber. So either it is the dimension of the ambient space, again, if it fills the ambient space, or the dimension of the parameter space minus the fiber. So the gauge subgroup minus the dimension of the stabilizer. Okay? Okay, so that's a first problem, which is the dimension of the stabilizer. So for this, we were very lucky. There was a result due by Dersken, Makam, and Walter that I'm not going to quote it in complete generality, but it says that the dimension of the stabilizer is 0 in most cases. And I just quote two important ones, two cases that are interesting from the physical point of view. The matrix product state, those that I've drawn already many times of these forms, and those that are called PEPs, so those that are kind of bricks, okay? And you can enlarge it, okay? Okay, so this helps us in many cases. And actually, the fact that for the matrix product state, that was exactly the dimension, so that the stabilizer was 0 and that there's nothing more in the fiber was again already known from Eggman, Marian, Osborne, and Verstraete. And so they computed the dimension of the tensor network variety every time that the network is a matrix product state. And this is exactly the bound that we have seen before, either the ambient space or the parameter space minus the gauge subgroup. So in that case, we have that result. The stabilizer is 0, there's nothing more in the fiber. So the second part of our result is the following. So what's up to here, I have already said. So the dimension of the tensor network is smaller or equal than everything minus the fiber. That every time that we have a graph with supercritical vertices, we have already seen that we can reduce it to be critical vertices, then we have that the stabilizer is 0 and that there is nothing more in the fiber. So every time that we have supercritical cases, the upper bound that we provided with this formula is reached, and moreover with a stabilizer that is 0. So this is actually our main thing. Okay, so what's left? Well, it's left to see what happens in the subcritical cases, in all the, so let's say better, in all the cases that are not supercritical. So for that cases, we start.
Sorry, can I?
Of course.
Interrupting. One is like the finite warning that I promised you, but also there's a question chat by Jianfeng Liu.
I'm sorry, I'm not looking at the chat.
No, that's why that's on me. And he just asked. They just asked whether you could remind them what supercritical meant, whether it meant that all vertices, whether every vertex is supercritical.
No, the definition is that you have a vertex that is supercritical. Yes. So it's the vertex that is supercritical. Okay. Every time that you have a vertex that is supercritical, then you can reduce it to a critical case by using this formula.
Thanks.
Okay. So in the other, in cases that are not supercritical, we have run many examples in the first cases. So this first table refers to a tensor network that is a triangle, and this other, it's a square. And in all the cases, all the bond dimensions, so all the weights that I have here, they are all 2. And so we let vary the dimension of the vector space incident here. So the n is a string of the dimension of the vertices of the vector spaces attached to each node. And so where I write upper bound, I computed the dimension of the parameter space minus the dimension of the gauge subgroup, and that's it, without counting anything more. So that's the upper bound. And this is the upper bound in this case and this case. And then when I write lower bound, what do we do? So we just take a random point in our tensor network variety. We have the parameterization. We compute the tangent space at that point. This is just a lower bound because it's just saying that we did not, reach eventually the dimension of the ambient space because we were not good enough to find a point that has the correct dimension. Since we had a random point, one may assume that this is a good hint that that's going to be the right answer, but it's just, we can only write lower bound. And as you see, every time that the lower bound agrees with the upper bound, and it's a proof that variety has exactly that dimension. But every time that we don't have the lower bound equal to the upper bound, we have to work more to prove that if there's actually that gap. And I like to highlight that all the cases where I put these stars are cases where the lower bound doesn't reach the upper bound. And so we prove it in some cases. If I have 1 minute more, I try to explain this case. Otherwise,
I think we started 2 minutes late, so you should go ahead.
Okay, good. So I try to explain the first, this orange case. So this is, as I said, the triangle 2, 2, 2. And the vector spaces here have dimension 2, 3, and 4. So the graph tensor sits inside the triple product of this C2 times C2, and the tensor network lives in C2, in the projectivization of C2, C3, C4. Now take any tensor in C2, C3, C4. It doesn't matter if it's in the tensor network variety or not. You can always make the first flattening. So you just flatten that tensor, thinking it as a matrix between C2 and C3 times C4. Now this is a matrix, and if you look at the image of this map, since you're starting with a C2, if it's not the 0 tensor, this is going to be either rank 1 or rank 2. You don't have any. So the image of this map is either a point or a line. Okay, so what we could show is that the tensor sits inside the tensor network if and only if, when you perform its first flattening, either you get a point or you get a line that intersect. Now you go in this space. In this space, you take all the matrices of rank at most 2. They are a set. I mean, they are a variety, but whatever. You take it and you consider all the lines that intersect this set in at least 2 points, counted with multiplicity. So it may be also tangent. Okay. And so it is in the tensor network, if and only if it represents one of these two cases. Sorry. I'm sorry. And now you count these dimensions, and this dimension is exactly 22. And 22 is smaller than 24. That was the upper bound. And that's the same proof also for this case. And we also proved another case for the square. Yes, is where the square case 2, 2, 2, 2, where all the n's were 2. And in that case, we were able to prove that the lower bound is again the correct dimension because it's an hypersurface, and we were able to describe that hypersurface. So that's it. I have the further questions. May I go with the further questions?
Yeah, maybe a quick rundown.
Okay, I'm sorry.
Maybe people can already think about questions they want to ask.
Yeah, so what's left? Left is to classify all the cases where the upper bound is not reached. And I like to underline this fact because it's a kind of general phenomenon in algebraic geometry that every time that you have a good parametrization of a variety, you have a kind of expected dimension. So you expect that the dimension is almost always the upper bound. And every time that dimension is not reached, there's some geometrical meaning. So some pathological effect in geometry that tells you that the dimension is lower than what you expect. So also from the geometrical point of view, it's going to be very interesting to classify these particular cases. And then one question, more general question, is given a tensor, find which is the best tensor network that where your tensor belongs to. Physicists may have a reasonable way to fix a graph and then moving the bound dimension, but I don't even know if it's that given. So if you maybe also change the graph and represent the tensor in a better way. Okay, so what's well established for them is that they have good procedure to find the approximations of the tensor on the tensor network variety that they want. Okay, I'm done. Thanks.